So we have torque and a current loop. Okay. Torque and a current loop, magnetic dipole. So torque and a current loop, magnetic dipole. Now we are going to place. See, these are the two poles of the magnet. So here we have, these are the two, this is split ring commutator and these are the brushes. Okay, you can say carbon brushes. Now this is connected to a battery like this. Now north pole, and this is B. This is a length and width is given to you, A and B. And this one is the rotation. The rotation is omega. Omega is the angular velocity. B is the width, A is the length, and B is the width. Now we have A, B, C, D. A, B, C, D. This is a coil, okay, rectangular coil. A, B, C, D is a rectangular coil placed between the two poles of the magnet, and this is the axis on which the coil rotates. A, B, C, D is the coil. It rotates on the axis. This is the axle. Dotted line is the axle. And the current is flowing through this wire. I is the current which is flowing through the wire. Now, what is happening? The magnetic field is in this direction. Magnetic field capital B from north pole to south pole. This is the direction of the magnetic field. Now, what is the torque? The torque is acting along the axle, and this is the magnetic moment. B is the, here small m is the magnetic moment. Like we have electric dipole moment P, we have magnetic dipole moment M. Okay. Now I is the current. I is the current through the thing. So therefore, we already know when a current carrying conductor is placed in a magnetic field, the formula is F1 is equal to BIL sin theta. BIL. What is the length? Length is B. Similarly, the second wire is also in the presence of magnetic field. That is also BIB. So here F1 will be equal to F2. F1 is equal to F2. Now, when the current is placed in the presence of magnetic field, what happens? Around it there is a magnetic field. Around it there is a magnetic field. The magnetic field is in this field. Maybe it is anti-clockwise. Here it will be. Here the magnetic field is clockwise. Here it is clockwise, and here it is anti-clockwise. So what happens? This magnetic field and this magnetic field, they repel each other. The magnetic field produced by the wire and the given magnetic field, they repel each other. Same way, the magnetic field around a current carrying conductor and this magnetic field, they repel each other. So because of this, because the magnets are fixed, they cannot move from this one, from their point, from their place. Only the coil can rotate. So this coil this moves upwards and this moves downwards. So there is a torque acting. The torque is acting along the, this is the magnetic field, tau is the torque. Torque is acting along the axle. And there is a resultant magnetic moment, that is N. So here, how much is the torque? Tau is equal to R cross F, force into perpendicular distance. Force into perpendicular distance. The perpendicular distance is A by 2. Half of the distance is A by 2. Plus, again, force into perpendicular distance. Now, what is force? Force is equal to BIB into A by 2 plus BIB into A by 2. So that will become what? Tau is equal to BIB into 2 times of A by 2. So that will become A. So this is what A and B is what? Length and width. So area is what? Area of a rectangle is length into width. So tau is equal to what? BIA. Is that clear? Tau is equal to BIA. Now, so we got this formula. If there are n number of terms, we write capital N. Tau is equal to NIAB. Now here we already know that magnetic moment is like I into A. Magnetic moment is I into A. This came from magnetism chapter. Okay. So magnetic moment is current into area. So we can write tau is equal to what? M cross B. So we can also write tau is equal to MB sin theta. Is that clear? Tau is equal to M cross B, which is equal to MB sin theta. Once again, from the beginning, see, here this is a coil which is placed between the two poles of the magnet, and this pole is connected, this coil is connected to the split ring commutator. In turn, it is connected to the brushes, and after that it is connected to a battery. And this coil is mounted on an axle. Okay, so what will happen? The length is B and width is A, and omega is the angular velocity. So what happens when you switch on, the current flows in this way. So when the current is going in this way, in this turn AB, in this arm AB, then around it there is a magnetic field. This magnetic field is in anti-clockwise. This magnetic field and this magnetic field, they repel each other. Similarly, this magnetic field and this magnetic field repel each other. So because of that, what will happen? The magnets can't move, but there is no linear motion. Only there can be a rotational motion. So the coil will rotate about the axis on which the axle on which the coil is mounted. And here, so what is our formula? When the current carrying conductor is placed in magnetic field, F1 is equal to BIB. Similarly, F2 is equal to also BIB. So if both the forces are equal, then tau is equal to what? Force into perpendicular distance. F1 into A by 2 plus F2 into A by 2. So what is F1? BIB into A by 2 plus BIB into A by 2. So that will become BIAB. So tau is equal to what? BIA, where area is length into width. So we can also write M. M is what? I into A, M cross B, or we can write MB sin theta. So this is the formula for, if there are n number of terms, we write tau is equal to NIAB. If in the coil, instead of one turn, there are n number of terms, we write tau is equal to NIAB. So we have the formula tau is equal to what? M cross B, or we can also write tau is equal to what? P cross E. These are the two formulas. Okay. Tau equal to M cross B, or tau is equal to P cross E. So what are the dimensions of the units? It is measured in ampere meter square. It is measured in ampere meter square. This is the formula. Is it clear, all of you? Are you
Yes, sir.
clear with this derivation? Huh? MB sin theta, yeah, MB sin because it is a cross product. Okay. So the next one is we have analog. Okay, electrostatic analog. Okay. Shall we continue, or you want to do tomorrow?
Sir, tomorrow is Sunday, right?
Yeah, tomorrow is holiday. So should I continue then? There's one more. After this, we have electrostatic analog that I have to teach. Then two more are there. That is about the MCG is there. Then the revolving electron of, what is that? Dipole moment of revolving electron
on the axis.
On the axis.
And then in MCG is galvanometer calculator and voltmeter.
So should I go ahead then? What do you say, Arham and Abid?
This one. Okay.
I'll go with electrostatic analog. Means how do we remember the magnetic statics formula with electrostatics? With electrostatic formula. That is the meaning of electrostatic analog. So we write P is equal to 2QA. Here we write M equal to I into A. Okay. Electric dipole moment formula, magnetic moment formula. Okay. And next one is, here we write 1 by epsilon 0. Here we write mu 0. Here we write electric field. Here we write magnetic field. And here that is axial line formula is EA is equal to 1 by 4 pi epsilon 0 into 2p by r cube. Here we write magnetic, for axial line we write mu 0 by 4 pi into 2m by r cube, 2m by x cube. This is the formula. Similarly, for equatorial line, we write 1 by 4 pi epsilon 0 into minus p by r cube. Okay, so here magnetic, this is equal to what? Mu 0 by 4 pi into m by x cube. Okay. Next is what we have tau is equal to what? P cross E. Here we have formula tau is equal to M cross P. And there one more formula is there. What is that? Energy, no?
This one.
Energy formula is there. No? Yeah, U is equal to what? P dot E minus P dot A. No? Yeah.
Yes, minus.
And here also it is minus M cross M dot B. So these are the formulas. If you learn one, you can remember the other one also. This is electrostatic analog. Now we'll quickly go to the next derivation. The next derivation is electrostatic, that is revolving magnetic dipole moment of a revolving electron. Magnetic dipole moment of a revolving electron. It's very simple also. Revolving electron. Okay. Magnetic dipole moment of a revolving electron. This is important. Okay. So like this is a nucleus and this is the first orbit. So nucleus is positive in charge, that is plus Ze, and electron is revolving in the orbit like this. So revolving electron revolving in around the nucleus is like a current flowing in the coil, circular coil. Is similar to that. And this is the magnetic field. This is going in and this is going, magnetic field going in, magnetic field coming out. So here magnetic moment is mu L. We are writing like this. Instead of writing M, we are writing mu L. Now the current is like I is equal to Q by T, E by T. Next one is we have relation between linear velocity and angular velocity. What is the formula? We have V is equal to R omega, and next formula is what? Omega equal to 2 pi nu, which also can be written as 2 pi by T, which can also be written as 2 pi by T. Now T is equal to what? T is equal to 2 pi by omega. Okay, T is equal to 2 pi by omega. But what is omega here? Omega is equal to V by R. Okay, so we write T 2 pi by V by R. So that can be written as 2 pi R by V. 2 pi R by V. Okay, 2 pi R by V. Now we are going to substitute this. Let it be equation number 1 and let this be equation number 2. Now substitute 2 in 1. Yeah. So what do we get? I is equal to what? E by 2 pi R by V. So this can be written as E into V divided by 2 pi R. Okay. Now what is magnetic moment formula? Instead of writing magnetic moment M is equal to I into A, we are writing mu here because M is the mass of the electron. That we have to take it. That's the reason. That is the only reason. We are not using, instead of taking M, we are taking mu L, orbital moment. So what is I is E V by 2M, 2 pi R into capital A. What is here A? A is the area. Area of the circle is pi R square. This R and this R will go away. Pi and pi will go away. The formula is EVR by 2. Okay, EVR by 2. Now again we have divide and multiply by M here. Divide and multiply by M. Mu L is equal to what? EVRM divided by 2M. Okay, divide and multiply by 2M. So what is MVR? MVR is equal to angular momentum. Okay, MVR is angular momentum. This we studied in last grade 11. MVR is angular momentum. So here we are writing MVR is nothing but MVR is L, E into L by 2M. This is the formula. Is that clear? That is the only reason why we haven't taken M here. Instead of taking M, we are taking mu L. Is that clear, all of you? Is it clear? See, once again, it is about magnetic dipole moment of a revolving electron.
So why didn't we take M? Like you told, we didn't take N something.
M.
Why didn't we do
M because M is the mass of electron.
Yes, sir.
So if you take M is the mass of electron, if you take it, so it will become confusion now. This here also it will become M. Both the side it will become M. Okay, so that
Yes, sir.
the meaning of M here is mass of electron.
Yes, sir.
Small
Yes,
m
sir.
is magnetic moment actually. Magnetic dipole.
Yes, sir.
So that is the only reason. So I is here, once again see, this is the electron moving around moving in the orbit. This is a nucleus, this is the electron. When electron is moving around the nucleus, it's like current flowing in the orbit. Okay, I is equal to Q by T. We have V is equal to R omega, omega equal to V by R, omega is equal to 2 pi nu, which is equal to 2 pi by T. Cross multiplied, V by R will go up, 2 in equation 2 in equation 1. We get this, okay. So we have M is equal to I into A, and mu L is equal to what? Mu L is equal to E into V, that is I into A. A is pi R square. We got this. So multiply and divide by M, then MVR is equal to what? Angular momentum. E into L by 2M. Okay. So here electron is negative, so I am taking minus. And the charge I am taking minus. Okay. So if you cross multiply this, mu L by L will be equal to E by 2M. E by 2M. This is said to be gyromagnetic ratio. This ratio is known as gyromagnetic ratio. Okay. Now, is it clear, all of you? This one?
Yes, sir.
Okay. So the next second part of this is The second part is, I write again, mu L by L equal to what? E by 2m, which is known as gyromagnetic ratio. Gyromagnetic means there are two motions at the same time. Gyromagnetic ratio. Like suppose the meaning is like I'm keeping one paper in this way, like this is the object. Like it happens in the machines. When I'm rotating here, when I'm rotating this one, then this will rotate. This is in the steering. You know, in the cars we have the steering. We rotate the steering and the tires will rotate in the other plane. Understood? Steering is in one plane and tires are in the other plane. These two are in different planes. This particular concept is known as gyromagnetic ratio. So here we also have the formula L is equal to what? NH by 2 pi, which is angular momentum. So H is what? 6 Planck's constant, 6.62 into 10 to the power of minus 32 joule second. This is the value. We are going to substitute this value. L is equal to what? Mu L is equal to what? Mu L is equal to L is what? Cross multiply, will multiply. That is L will cross multiply E into L by 2 pi, which is equal to E into NH by 2 pi. Here one more 2 pi will come. So that will become how much? It is only M, sorry. 2m into 2 pi. So that will become E NH by 4 pi M. This is the formula we got. We substitute all the values and we get for the when n is equal to 1 first orbit, the value is 9.27 into 10 to the power of minus 24 ampere meter square. This value is known as Bohr magneton. This value is known as Bohr magneton. That's it. This completes your derivation. Last one is about the MCG, moving coil galvanometer. Okay, that I will teach tomorrow with the numericals, conversions and all is there. Okay, any doubt in this one? From where this came? This came from Bohr's postulates. Bohr's postulates. Okay, clear? Bohr's postulates. It says that MBR is equal to what? NH by 2 pi. From there we got angular momentum L is equal to MBR by 2 pi. MBR is equal to NH by 2 pi. From there we got it. Okay, so the angular momentum formula is given. Substitute the values, we'll get the answer. Is this clear all of you? Is it clear all of you?
Yes, sir.
Condition.
Yeah, Bohr's quantization condition. This condition is known as Bohr's quantization condition. This both
Discreteness of
the angular momentum is balanced.
the discreteness conditions